Welcome back. Here's the attendance. So we can start with the first chapter that is entitled Newton. Okay? And you can see this, right? Or do we need an increase in font? Would be better? I have no idea how to increase font, so. Huh? Command'e basıp yaklaştırın. No. How about this? Is it better? Okay. So, how do we start? Let's start with this. Import numpy as np. Okay? So, okay. Let's say you want to find sine of 5. Okay? And to run it, I have to press Shift Enter. You see, sine is not defined. If you run this in MATLAB, it is defined, right? Now, sine is not coming with the package here. All those mathematical stuff are inside NumPy. There are other things that you can use, but you should use NumPy, at least in this course. And this NP is just, everyone calls it NP. Okay? It's like a language that have evolved, and everybody calls it NP, but you can call it something else, but don't. Okay? How about this one? This is all about plotting. Okay? So maybe I can add some comments. All kinds of maths is here, and this is plotting. This is for plotting. Okay? Then let me just do this. Okay? Let me run these two. I did run this too. And let me write np sine. Now it will give me something. It actually gives me the value. So what is sine 0? It's supposed to be 0. It is 0. What is sine pi? How do you get pi? You write np.pi. What is sine of pi? Also 0, but here it's almost 0. And pi over 2, sine pi over 2 is 1. Everything is fine? Good. Now, let's do something. What is this doing? Anyone, can you tell me? What is this thing is doing? Creating an array from exactly. Very good. So it goes from 0 to 10. Does it go to actually to 10 or does it not? It stops at 9.9. Okay, that's the weird thing. When you count in Python, you start like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you stop. Like that's counting up to 10. So you remove the last one, but you add the 0 at the beginning. Good? Am I going too slow? Fine, right? So this is an array that goes from 0 to almost 10, and this is x, this is y, which is npi sine x, and when we plot it, you get this nice plot. Let me clear all the outputs so that we don't ruin the surprises, right? So far, how are we doing? Good. Now, some warm-up exercises. Let's say you want to write a code that finds prime numbers. Okay? Let me start here with the prime numbers. So it's MSN 514, chapter 01, Newton, right? And let's start with prime numbers code. So It's a very inefficient code that we have here, but let me explain what's going on. Let's say you want to know whether 10 is prime or not. Okay? Basically what this code is doing is it's actually, let me use 107, okay, which is better. So we look whether it is divisible by 2, whether it's divisible by 3, 4, 5. Let's say we are doing a very bad coding right now, okay? But even at that very bad coding, do we need to actually go all the way to 107, or is there a slightly smart way of doing it?
11 would suffice.
11
would suffice.
11 would suffice. Why?
Because every non-prime number has a prime factor that's smaller than its square root.
Every prime number has...
Every non-prime number, sorry.
So, like, for example, for 10, it's divisible by 1, divisible by 2, divisible by 5, and divisible by 10, right? But these two are coming after square root of 10, and these two are coming before square root of 10. And they are all one-to-one matching, right? So if you check up to square root of that number, it's enough, okay? Good? So that's what this code is doing. So this is how you define functions. This is a function that returns, okay, true or false. It returns true if the number is prime. It returns false if the number is not prime. So what does it do? If the number is smaller than 2, then it's not prime. Okay? Then let's understand this line. What is this line doing? It starts from 2 and all the way to, this is square root of that number. Do you see how it is written? Yeah? Square root of that number, and then you you make it an integer, okay? I tried to figure out a verb for it, integerify it, but it doesn't.
Integerize it.
Integerize is better. Then why do we have plus 1?
Because if it has a comma part, then it just reads the part after comma. So in order to find the integer that's greater than it, we need to add 1.
Right? You also were saying the same thing. You remember how we counted? We don't count the last one, so it adds one more so that the last one is also counted. Good? So for all, whatever. I mean, we are whatever we have here, we are trying to understand. Yes. Well, if any of those, this is mode, okay? Number mode, that chosen number. If it's 0, then it's divisible by one of those numbers, so it's immediately false. If none of them succeeded to divide that number, then this number is prime. Are we going too slow? Too fast? It is fine. Good. Now, then what this one is doing, it's finding prime numbers up to the number n. As you can see, okay, here I need to explain you what this append is doing. So you start with an empty set, just emptiness, nothing in it. And you start numbers running from 2 to n, right? And for each one, it's running this function and figuring out whether it's prime or not. If it is prime, then it's adding it to this list. So you start a list with emptiness. Every time you find a prime number, you add that to the list, and then you return those prime numbers. And finally, we are running this code, this function up to 100, and let's see what happens. It gives us a list of numbers, prime numbers up to 100. If we do it for 1,000, it will return numbers up to 1,000, all of them prime. Okay? So far, so good? Okay. Another warm-up exercise. So it's a nice problem. So let me describe you the problem. You start with any number, pick any number. Let's go with 7. 7 is tricky, but let's go with 7. So if it's odd, then you do 3 times that number plus 1. What do you get? 22. If it's even, then you divide by 2. So 11, right? So what is the next number?
34.
34. Next number? 17. Next number? 52. Next number?
26, 13, 14.
Yes? 20. 10. 5. 16.
And done.
And done. Very good. Because we are done because this will enter a loop. Okay? Are you happy? Now, the Collatz conjecture tells us that no matter what the number you start, you end up in this loop. Okay? That's the conjecture. It hasn't been proven, and one of the very famous mathematicians, let's just deviate to some other stuff. So Collatz conjecture. Let's first know who Paul Erdős is. One of the most prolific mathematicians and producers of mathematical conjectures. The oddball's oddball. I think, okay. Erdős published around 1,500 mathematical papers during his lifetime, a few that remains unsurpassed. Okay? A mathematician with the most number of papers. And what did he say about Collatz conjecture? Mathematics may not be ready for such problems. Okay? So, could be that the definition of Collatz conjecture is very easy and it's very easy to understand, but apparently proving it is really, really hard. Okay, so let's do the following. We are going to analyze the code that creates this plot. Starting number versus number of steps to reach 1. So what was the number for this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So for 7, we are going to have 16 here. Okay? So far, so good? Is this pointless? Are you having fun? Good. So define Collatz steps. Number of steps is 0, while n is not 1. So we start with n, while n is not 1. If n is divisible by 2, then divide it by 2. This one divides by 2, but it returns an integer. Okay? It's different from just n divided by 2. Just one slash will give you a real number, and it will create some problems. But if you do 2 slashes, then it's an integer. Okay? Good. If it's integer like that, if it's even, you divide by 2. If it's odd, you do this 3m plus 1. And you increment this number of steps. And finally, you return the number of steps. Okay? Then what do we have here? we have some n starting numbers. Okay, it generates a list using this range function. Did we talk about range? Range was here. So when you do for number in range, you can use just the range by itself. But what range creates is not a list. What range creates is a range object. Don't ask me why, okay? So if you want to deal with list that corresponds to that range object, you should put it in parentheses like this, and you should make it a list. Long story short, this creates a list of starting numbers that goes from 1 to n. Good?
I have a question.
Yes.
What happens when the upper bound of the range is not an integer?
Then I presume that it go. Let's try. So you want me to create a list and range starting from 1 all the way to 9.3, right? My guess is it will stop at 9. I was wrong. Range wants it to be actually integer. But what if you do it like this and you put also an increment? Then I think it will work. Oops. It doesn't work. Okay. So for range, this doesn't work. Anyone who knows how to fix this?
You use
NP arrange, yes. Like if you need real numbers that go like this, we have already used it. Do you remember? NP arrange. So whenever you need that, you just use NP arrange. So let's just erase this, NP arrange. Then it will create what you need. Are you happy? Yeah, me too. Good. So this is a scatter plot, and I got its logarithm, but let's not start with the logarithm. Let's go like this. Okay. So what do we have here? Steps list. So basically what it does is it goes for all numbers in this list, starting numbers, it gets this number and puts it in the Collatz steps function and creates you a list of steps. Did you follow this? Yes?
Yeah.
So, and then you just create a plot. Let's run this, and it creates this nice, beautiful plot. And you can see why it can't be solved now. It is lifelike. I mean, it's weird. It's not like triangles, squares, and whatnot. If you want to make it a bit linear, then you can just let me Control Z and go back to, yeah. Now I have the logarithm. Do you see? If I take the logarithm of this side, then you are going to get something like this. Looks better, but it still has a lot of peculiarities. Okay. Now what you can't do is zoom on it in here. So if you want to always be able to zoom, there are two options. Okay, let me show you the first option first before I break all the codes. So if you want to zoom, you can use Plotly. Did I write this code? Of course not, right? I just asked the computer to write this code. So I don't know by heart what's going on here. But what it is using is this library called Plotly, and it creates HTML file as an output. Let's run it. And it will open that HTML file. What you have seen before in the plot now is here. And you can zoom on it, and you can see the intricacies. Okay? And it's a nice way to save your plots for future, whereby you can return and just open it in your web browser. Okay? and see what's going on in the plot. But you can see the intricacies here, and you can see that there seems to be a pattern, then it is gone, etc. Okay? All right. What is the second option? The second option is you write here widget, right? And you start with that. Then your plots are plotted differently, and you get these zooming options. Okay? But it's not super. I mean, let's run this here also. I wouldn't call it super efficient, but it works. Okay? Do you have any questions, comments? What? What do you mean? Widget? Notebook. Yes? Cannot change to different view. Restart the kernel. Okay. He wants me to my code to break down. Let's see. Okay. Yeah. Okay. Where is it? Huh? Okay. So let me go back to inline. Hopefully that will work. Yeah. Okay. Now we are warmed up for the chapter. Let's start with an easy problem. Let's just simulate a bouncing ball. Okay, using Euler's method. So what do we have for the bouncing ball? We have gravitational acceleration. It's basically m d squared x over dt squared is, it's actually this, right? That's it. A ball that is falling down. Free fall. Any questions here? No. Now, I want to implement also the condition for the floor. Okay? The way that I'm going to implement it is that whenever it reaches here, whenever the ball is here, I will say that, okay, let me look at the code, what I called it. I called it h, okay? Whenever h, let's say this distance is h, and this, let's say this is 0. If h is 0, if h is less than 0, and also its velocity is less than 0, meaning that if it has reached the ground, but it is still going down, then you should reverse the velocity. Sometimes in gaming community, they would not only reverse the velocity, but they would also put h to exactly 0, so that it doesn't go inside the wall, so it doesn't seem unphysical. But in our course, it actually creates unphysicality, because then you don't conserve the energy. You know, you artificially add a potential energy there. So we are not going to do that. We are just going to do this. V equals to minus V. Was this clear to everyone? Now, how do you implement second order differential equation in a computer? Well, you turn it into a first order differential equation. So you know that velocity is dx over dt, right? and the change in the velocity will be minus g. Okay? The simplest way to attack this is to write. So what is dx? Dx is basically change in x, right? So it tells you that dx is v times dt. So if you choose some delta t, let's choose a numerical value delta t equals to 0.01, for example, then this corresponds to x equals to x plus v times delta t. Is it clear to everyone? Or in our case, h. Everything here, let me not change it. Let me just leave it x, and you do understand everything, right? How about the velocity? Velocity is equal to velocity plus, and the acceleration is minus g times delta t. Does it matter if you write this one first in the code or this one first in the code? Will it matter?
Yes.
Yes, why?
Because this updates v after x, adding another second order term, the other one doesn't.
So which one is correct? Which one is logically correct? Did you understand the explanation? So let's look at the two cases.
Seems more reasonable.
So v times delta t and v equals to v plus, let me just straight ahead write it, g delta t. The first case is this one. The second case is this one. So you see, what it tells you is x next is x old, v old times delta t. What this one is saying is x, let me not write it next, it's new. New, this is old, and yeah, that's pretty much it. So, and if we don't write this old or new, you see, this one is logical because you are using the old v, the old x, you are getting the new x, and then you are updating the old v to new v. So far, so good? But here, you first update the old v to new v, and then you use actually new v and old x to get the new x. You see, this is logically wrong.
Why not use the average of this average velocity?
We will come there. We will come there. So this is the correct way of using Euler's method. But interestingly, well, let's come there. Let's come to that point, and we will see. So let's see what is going on in this code. You have the acceleration, you have time step, the initial height, the initial velocity. Then you have a bunch of empty lists to which we will append the values as we find them. Okay? So we initialize the Euler simulation. We set t equals to 0, initial time, initial height, initial velocity, and then we append those values to t values, h values, v values. So far, so good? Then let's update them. Please don't see this line. Okay, it's a surprise. So h goes to h plus v delta t, v goes to v minus g delta t, right? This is the correct way to implement, and check for collision with the ground if h is less than 0 and v is less than 0. And you see here, this one is not a good idea, right? Let's check all this. This is the reverse, and let's plot what we get. Do you see the problem? It's a magic ball that keeps jumping higher and higher, right? Did we do anything wrong? No. It's a fundamental flaw of Euler's method. When you have this kind of linear systems where the energy is supposed to be conserved, and it just simply doesn't. Okay? You need to figure out a way to go to higher orders or somehow to get rid of this. Let me do this. Let me do it the wrong way. Okay? For a moment. Let's run it. And when you do it the wrong way, it actually seems more natural, but this is wrong. Okay? Very good. So we have applied Euler's method and we have failed. Okay? I will talk about this condition once we fix this problem. We haven't fixed this problem yet. Let's animate the bouncing, and I'm not good at this so far. I haven't figured out a best way of animating, but you can see the animation here. Boom. Goes higher. Boom. Goes even higher. Even higher, etc. It's not very clear whether it goes higher or not, but it clearly does because it started at 1. Okay? All right. So let's move on. We will come back to bouncing ball in a minute, and we will solve it. We will solve our problem. Let's talk about harmonic oscillator. Why I am laughing? Because, yes, they have a hopefully good memory of it. We kept coming back to harmonic oscillator in the previous course, and there's a good reason. Harmonic oscillator is almost everything is a harmonic oscillator. So let's draw a simple harmonic oscillator like this. What is the equation? M d squared x over dt squared equals minus kx, right? How are you going to simulate this one? Well, the same way, right? X, help me out here. X equals to x plus v delta t, and v equals to v plus, this time, minus kx over m delta t. But this should be x old, right? Did you get it, or was it too fast? You got it, right? Let's see how we implemented it in the code. So what we do is we find the acceleration, so we don't have that problem of x being old or new. Since we calculate acceleration as a separate variable, it depends. It is found by the previous x anyways, right? Let's run harmonic oscillator. What do you expect from harmonic oscillator? Go back and forth, right? Let's run it. Same problem here. Do you see? So Euler's method doesn't work for this one as well. Doesn't it work like ever? No, it does work, especially in the systems, in those nonlinear systems that we are going to see, some of them. Okay, the well-behaving nonlinear systems, like your heartbeat. Okay, if your heartbeat starts acting out, it has mechanisms that brings it back to itself, right? So you can actually simulate your heartbeat with Euler's method, and it would be just fine, because it has a limit cycle. It brings it back to its original beating. But these kinds of oscillations where the energy is conserved, this Euler algorithm fails badly. You have a question?
Is the increase in the energy due to Euler algorithm linear or exponential?
It's quadratic, I think, in delta t. That's a very good point. Let's try doing the following. Let's fix this first, and let's plot the difference between two solutions once it is fixed. Are you with me? Yes? Good. Now, what is the solution? I like this solution. There are other solutions as well, but this is the simplest addition to the problem, and you basically solve it. And the solution is Verlet integration. Should I derive it?
Yes, please.
Come on. When a teacher asks, should I derive it? What do you say? No, please. Gerçi burada yapılmışı var. Anyways. I could show you from previous years. If I can't do it, I will show it from previous years. So, Taylor expansion, right? And then there is this jerk. It's called jerk, the third derivative. Okay, t cubed over 6?
6.
Very good. So let's write down the same thing for v. And for a. Okay. So what do we do next? Anyone remembers? So what you do is you take this jerk and take this from this equation and plug it in the other equation. Okay? What is the jerk?
A plus delta t minus at.
Exactly. So what I did is I've written it up to the third order, right? For every equation, to the same order for every equation. And now I'm going to plug this one in here, right? Okay, help me out. What do we get here? I think we get this. Did we?
Yes.
Yes? Yes? Everyone is happy? So, let me write it down here, and let me just take this part only and put it here. Okay, let's say you are doing harmonic oscillator. In harmonic oscillator, your acceleration depends on the distance. It doesn't depend on velocity. Do you agree with that?
Yes.
Yes? So what you do is you find the next x by going to the next level here. Can you do that? Yes, you can, because you can find at from minus k over m times x at t, right? Yes?
Yeah.
Now that you know x at t plus delta t, what you can do is you can figure out a t plus delta t at the next time. Did you get it?
Yes.
Yes? Now that you know this, you can plug it in here. The general name for what we are doing here is called predictor corrector. So we predict what's going to happen next, and we use that prediction to correct what's happening now. Some of you seem confused. Can you please ask me questions? Yes.
What if our acceleration also depends on velocity?
Yeah, very good. Very good. We will encounter such a case, and I will tell you what to do. Which is probably wrong, but it works. I will show you. Any other questions? Amna? Are you sure? You seem confused.
No, I don't have any questions. I'm just taking everything in.
Okay, okay. All right. Let's see how we implemented this. Same code. You just have the acceleration part here, and then you derive x from there by including a delta t squared over 2, right? But then you have the next a, and then you have the average of acceleration used to move on. Just like you said. I forgot your name. What was your name? Abdullah said. Right? You said something about averaging it out. So let's run this one. Do you see? It's perfect. Are you happy? Yes? Good. Now let's go back and fix the bouncing ball. How do we fix the bouncing ball now? What do we need to add to this? Now we are going to use Verlet. Well, what we do is we just add this acceleration term, right? But we don't need to do anything over here because it's constant, right? So acceleration is always constant. So in the next generation, it's still minus g, so this shouldn't change. But hopefully, this will fix our problem. Does it? It does. Do you see? It's perfectly going back to the same energy. Now, if you were to put this gaming thing here, right? Putting it back to h equals to 0, then it would overshoot on the other end, right? So we are not doing that. But yeah, it's annoying when in FIFA legs go into the heads, etc., like that kind of stuff. So to avoid that, you have this this kind of stuff. Good. Animate the bouncing. I'm adding 0.1 here, okay? So it's not starting from the center is not at 1, but the bottom is at 1 of this ball. Yes, okay, it bounces to the same place. Let it bounce. Is it a good place to have a break or yes? Let's have a break. Ne? Shift enter.